Well, good morning and welcome back. I hope you're all doing well. It's March 30th. This is the month that would not end, but it will end on Wednesday. It'll be April 1st and we'll be all done with March. And I hope April will be a better month. Um, I'm doing okay. I had a good day yesterday. I was able to buy toilet paper from Walmart, so that was a big thing in my life, really. So I hope you too are able to remain stocked in all the essential items. Thanks to Charlie for posting a good video on the Kissimmee River. And lots of you have posted really intelligent and good questions and comments about that. And Charlie has responded in a terrific way. If you haven't posted anything in response to his video, you still have time to do that. So that's on Notebowl Bulletin. Watch the video and then give Charlie something to think about and respond to. Make him work for his grade. So far that has worked really well. Thanks to you all. So now we're moving into lakes. Last week was stream week, and now we're going to talk about lakes. So this is in the FE, Freshwater Ecology book, chapters 6 and 22. And then we're still hanging out in Protected Land book, chapter 9. We're looking forward to a presentation from Henry this week on Wednesday about lakes. And Charlie has set the bar pretty high, so you're going to have to work pretty hard to top Charlie, I think. Okay, so let's talk about lakes. Just like with streams, we have to first talk about a number of zones and names and things like that to get you oriented to learning about lakes. So here, this top picture is a picture of lake that shows some of the different zone names you should know. So first of all, when you are near the banks of the lake in the shallow waters, we call that the littoral zone. Some people call it the littoral zone. That is just the zone where it's shallow enough that plants can be rooted in the soil or substrate and still get sunlight to grow. If you're out in the deeper waters, the open waters, that's called the pelagic zone. And then kind of going downward into the depths of the lake, we have the photic zone where light can penetrate. And then down here, the aphotic zone, where it's too deep. You have to be in quite a deep lake to get an aphotic zone where sunlight can't penetrate. You see some other terms over here, especially this thermocline. We'll talk about that more in a second. This bottom diagram is talking about what we call stratified lakes. So these are layers of the lake that develop based on their temperature and density. So this is showing a summer day. And this upper part of the water, the upper part of the lake is called the epilimnion. So epi means outer, like epidermis on your skin, the outer layer of your skin, and limnion means lake, so that's the outer layer of the lake. I'll jump down to hypolimnion. Down here, the bottom waters in a stratified lake are called the hypolimnion, like hypodermic needle goes beneath your skin. This water is beneath. You see a zone here, a thin zone called the thermocline, and it is also shown in this top diagram here, the thermocline. That is a zone of rapid temperature change. You might have encountered a thermocline if you're a person that likes to swim in lakes. And if you've ever been out on a nice summer day swimming in a lake and you decided to go down really deep as you could, you might have hit a zone of really cold water suddenly. And that is the thermocline. We'll talk about why that develops in a second. The very bottom of the lake is called the benthic zone, or the benthos. And there are actually scientists and whole conferences and journals devoted to benthic aspects of ecosystems. So benthic ecologists study things on the very bottom of a lake. Pretty crazy group of people. Okay. So let's talk a little bit more about this stratification. So limnologists, people that study lakes, like to draw graphs like this, so that the y-axis is showing the depth of the lake going downward like this, so that this is the surface of the lake right here. And then this would be the thermal profile of a lake. So it's showing the temperature on the x-axis. So again, let's imagine this is a summer day in the Midwestern United States. Ohio doesn't have any lakes that are this nice. So let's imagine this is in Michigan or Minnesota or Wisconsin or maybe out west somewhere. But it's in a temperate part of the world. On a nice summer day, you get the upper waters of the lake, the epilimnion, warming up more than the deep waters of the lake. So you get a temperature profile that looks like this, warm water up here, and then as you go down, you hit that thermocline and the temperature starts to drop. And then when you're past the thermocline, you're into the colder waters. So interesting property about water is that it is at its most dense when it is at 4 degrees Celsius. So that is actually kind of an important fact, because a lot of substances are at its most dense when they are solids, but that's not true for water. Solid water, ice, floats on top of water that's not frozen. So that's actually a really important reason why life developed as it did on Earth, because if ice was the most dense form of water, lakes would freeze from the bottom up. So when we had ice ages or just winter, all of our lakes would be frozen solid, but that's not how it works. The ice floats on top and acts as sort of a skin on the lake, and then there's liquid water down all the way to the bottom that really doesn't get much colder than 4 degrees Celsius. So things can live in that. Some things go dormant, but a lot of things live just fine in 4 degrees Celsius water. Okay, so back to our thermal profile. Since water is at its most dense at its coldest 4 degrees Celsius here, this is showing it slightly warmer than 4 degrees Celsius because it's in the summer, but still that's the most dense form of water in this lake, so it's at the bottom. And the warmer water up here in the epilimnion is less dense, so it sits on top of that hypolimnion. So we get these layers of a lake. We call it lake stratification. Here's just another picture of the same thing. So here's a thermal profile of a lake in the summer. You see the warm waters of the epilimnion, the thermocline, and then colder waters at the bottom. If we imagine this, let's say a nice August day, and then we move into, say, September, this line is going to start to change. Now the days aren't quite as warm, the nights are a little cooler. Our line might look like this. Now we're getting into October, maybe the line looks like this. And maybe we're into late October, the line looks like this. Now we're into maybe early November, and you might get to a stage where the upper waters of the lake are the same temperatures as the bottom waters. At that stage, everything would be the same temperature and the same density, and that's an important point. We'll come back to that in a second. Now we move into, let's say, December and January, and now it's very cold out and ice forms at the surface of the lake, and we get this sort of inverted curve like this, where still the bottom waters of the lake are 4 degrees Celsius about, and the upper waters of the lake are colder than that, but they're still less dense, so they still float on top. So this is called seasonal stratification, and it brings up two important events that happen in a lake in our latitude. So once again, here's just another picture showing you epilimnion, the upper waters, how they can be less dense and sit on top of the other layers. This thermocline is sometimes called the metalimnion, the middle lake, and then we have the hypolimnion down here, the colder, denser waters. Okay, so this picture is showing you throughout the season. Let's start up here in the summer where we have started everything else. So there's our epilimnion, the warm waters of the lake, thermocline, and the hypolimnion. You see the epilimnion here is maybe 20 or 22 degrees Celsius, much warmer, much less dense. When we get to that day in late October, early November, I was talking about, and everything is now 4 degrees Celsius. You see all the temperatures are the same now. All the waters of the lake can mix. So we get this process called overturn, or sometimes people call it turnover. That means that, kind of like a big wash machine, all of the waters of the lake can mix. That means deeper waters that have lots of detritus, maybe less oxygen, can come to the surface. Surface waters that have a lot of oxygen can go to the bottom. This is a big event in a lake. This is actually a disturbance in a lake. If you've ever wondered how lakes can have a disturbance, this is it. This is the lake turnover event, and it sort of upsets the apple cart, and it changes things for the organisms, and they have to adapt to it, just like a forest fire would in a forest. My picture is obscuring this bottom diagram here, but this is showing the winter where there's ice on the lake. And so stratification has happened again in the winter. And then you get to the spring, where again, you get to a point where the ice is melted, the surface waters warm up a little bit, and now everything is 4 degrees Celsius again, and you get a second turnover event, or overturn event. This is called the spring turnover. So in our latitude, our part of the world, we have what are called dimictic lakes. That means they mix twice. They mix once in the fall and once in the spring. In other parts of the world, for example, in tropical areas, you could have a polymictic lake. These warm up and cool down so much every day that they're basically mixing every day. So they're polymictic. You could have amictic lakes, which are frozen all year round, like in Antarctica, and they never mix. You could have a monomictic lake that only mixes once. This might be, let's say, northern Alaska, where the lake ice only melts for a short time during the summer, and it has a mixing event, and then the ice forms again. So it only mixes once out of the year. So we happen to live in a part of the world where we get lakes that mix twice. Now, I will say very shallow lakes like farm ponds and things like that might mix every day in the summer just because they don't have the depth. Sunlight can penetrate all the way to the bottom, and their hypolimnion warms up really quickly. So a very, very shallow pond doesn't quite behave this way. You need a deeper lake that can develop a hypolimnion in order to get the dimictic effect. Good. Okay, let's lay on top of this the idea of different trophic states. So we've already talked about these terms a little bit. This is an oligotrophic lake, so low nutrient, blue water, excuse me, relatively low algae, relatively low productivity. These are some of the most beautiful lakes in the world. You see the mountainscape around it. There's not a lot of human development, and that's probably one of the reasons why it's an oligotrophic lake. Versus this sort of lake, this looks like Ohio. This looks like home to me. This is a eutrophic lake. It's got a lot of nutrients. It's got a lot of algae growth. It's got an interesting green color. It probably has an interesting odor. You would probably notice the odor before you saw the lake. And of course, you see a lot of human development around the lake. So humans, of course, tend to push lakes from an oligotrophic state. Both of these are natural, by the way. So eutrophic lakes can be natural, and oligotrophic and mesotrophic lakes are in the middle. They can be natural too. But humans tend to push lakes in this direction, from oligotrophic toward eutrophic, because we are pretty sloppy with our nutrients. We fertilize our farms and our lawns, and our septic systems leak and our sewage systems leak, and they bleed nutrients into our lakes, and we drive them toward a eutrophic or a hyper-eutrophic state. I think we've talked about that already. This table just compares some of the characteristics of eutrophic and an oligotrophic lake. So you see eutrophic lakes tend to be shallower. They have way more productivity than oligotrophic lakes. They tend to have way more nutrients. If you compare the N and P numbers here, oligotrophic lakes are very low in nutrients. Eutrophic lakes tend to have a lot of oxygen at the surface, but almost none in the depths. Oligotrophic lakes have oxygen all the way down, usually. The species are a little bit different too. So for planktonic species like algae, high numbers but few species in a eutrophic lake, many species but low numbers in an oligotrophic lake. And then fish, a lot of times we find many species in a eutrophic lake and fewer in a oligotrophic lake. Although I will say if a eutrophic lake gets so polluted with algae and nutrients that there's no oxygen in the water, then species of fish can't live there. So that's when you start to see a decline in species. So you certainly don't have to memorize these numbers or anything, just kind of know the basic difference between eutrophic and oligotrophic. So let's lay this idea on top of our lake stratification idea. So here is our thermal curve, once again, going down into the depth. And this is a curve for a stratified lake. This is an oligotrophic lake. So if we look at the oxygen profile of this lake, we can see that even though it changes a little bit as you go down in the depth, there's oxygen present all the way down. And that's the main, there are other lines on these graphs, but that's the main thing I want you to see. That in an oligotrophic lake, even when it stratifies, there's oxygen all the way down. Very different in a eutrophic lake. Excuse me. So here is a temperature profile stratified eutrophic lake. Look what happens to the oxygen. There's oxygen present in the epilimnion, and then it drops off the table, goes to 0, and there's no oxygen down here at depth. Why is that? Well, in the upper waters, the epilimnion, there's a lot of algae. They're doing photosynthesis. oxygen is given off in photosynthesis. So that's the source of oxygen here. Down in the depth, there's no photosynthesis happening. In fact, there's a lot of dead, decaying algae, and so there's a lot of respiration happening that takes up oxygen. So in a eutrophic lake, when it stratifies, you get this real oxygen difference. Oxygen present at the surface and no oxygen. This is called an anoxic environment. Down at the depth, there's no oxygen available. Okay, so there's a lot of graphs that show these depth profiles. I'll throw a couple more at you here. A oligotrophic lake, this little theta here represents the temperature. So you'll notice the same S-shaped temperature curve here. So in an oligotrophic lake, we have this stratification event. You see our oxygen stays pretty much the same all the way down. pH stays pretty much the same all the way down. And CO2 stays pretty much the same all the way down. So a turnover event is not as big a deal for an oligotrophic lake. You're mixing water from the bottom that's very similar to water at the top. Eutrophic lake, very different. So here's our temperature curve again. And you see the oxygen dropping off the table as you go down in the depth for reasons we just talked about. CO2 goes up for the same reason, because there's a lot of photosynthesis at the surface taking up the CO2, but down in the depth, you get a lot of respiration giving off CO2. And pH changes too. So if you look, here's the pH curve. And the pH actually gets a lot lower. In other words, it gets more acidic down at the depth. Because you're giving off all this CO2, you're making carbonic acid. So this is not acidic enough that it would harm you or anything like that, but it's a measurable difference. If you're a fish or an organism, it might be a big deal to you. Down in the depths, you have a lower pH, you have less oxygen, you have more CO2. So a turnover event here in the fall or spring is a huge deal because it's bringing up water to the surface that's very different than water down below. Okay, so we're going to look at some nutrients on top of these also. We'll take a quick look at nitrogen. Nitrogen has some different forms, as you'll remember from earlier in the class. And in an oligotrophic lake, because oxygen is pretty much consistent from top to bottom, even when it's stratified, mostly the form of nitrogen that's available is nitrate, NO3 with a minus. Not very much ammonium. Nitrate is the form that's available when oxygen is present, if you remember that. In a eutrophic lake, because we get this oxygen dropping off the table here at the thermocline, there's nitrate present in the surface waters because there's oxygen present, but it really goes to zero. And down in the depths, we have ammonium. That's an anoxic form of nitrogen that's abundant down here. So again, if this might not be a big deal to humans, if you were diving down in this lake, you wouldn't notice it. But if you're an organism that needs a certain kind of nitrogen, this is a huge deal because where you are in the lake, the type of form of nitrogen changes. So we talked about this a little bit, but in some lakes, especially eutrophic lakes, you can get an invasion of an organism called cyanobacteria. Cyanobacteria are a type of algae. They form these kind of sheen, oil sheeny type mats on top of the surface. And they're kind of insidious in a couple respects, but one is that they have the ability to fix nitrogen. If you remember what that is, I hope you do. That means they can turn N2 gas from the atmosphere into ammonium. And so they can bring their own nitrogen with them. And so you get, in some cases, here's a picture of Lake Erie, and you guys know this story probably if you've been paying attention. A lot of years we get an algae bloom, especially in the late summer in Lake Erie, because it's surrounded by farmland and industry and septic systems and things like that that are bleeding nutrients, especially phosphorus, into the lake. So it's already eutrophic. And then we get a cyanobacteria invasion with sometimes other types of bacteria that are toxic as well. And we get these big algae blooms. And the algae blooms are, of course, blocking sunlight and creating detritus and using up oxygen and all that. They're also bringing in nitrogen, kind of exacerbating the problem. And one difficulty that Lake Erie faces is that this happens on an annual basis. Some years it's not as bad as others, but it's a very difficult problem to get rid of. Once you guys know the word hysteresis already, once you've sort of made the journey from oligotrophic to eutrophic, it's very difficult to reverse that. Now, Lake Erie was probably never a very oligotrophic lake. It's shallow, it's surrounded by land that is erodible, it's already kind of high nutrient. Humans have really pushed it toward a more eutrophic state. And if you live in Toledo or Northwest Ohio or anywhere in this area in the western basin of Lake Erie, this is your drinking water source. So this is a concern for a lot of people. And it's a lake that has ended up in a eutrophic state. I will say in Lake Erie, if you're standing in the right place at the right time, you can actually notice the turnover event happening, especially in the fall, sometimes in the spring as well. But it's a dimictic lake, so it mixes twice. And in that fall turnover event, lots of water that's filled with kind of black gunk comes up from the bottom, washes up to the surface, and adds to this algae bloom because it brings up lots of nutrients to the surface. And if it's still warmish in October, there's plenty of time for another bloom of algae to grow. So Lake Erie, because of its geography and its shape and its basin depth, it's set up to really have some problems because humans have really loaded it with a lot of nutrients. Okay, we'll pick up with this next time, but we'll stop there, and I will talk to you on Wednesday.